Chapter 20 is about hypothesis testing, similar to what you would go through if you were in a science class and you were learning how to test a hypothesis there. Our focus in this chapter is going to be only on proportions, so percentages, and we're going to break down the different steps as we go and do several examples. So we're actually going to look at the example to start with so that we have a baseline of information in order to go through all of the steps of a hypothesis. So here's our situation. Ingots are huge pieces of metal made in a giant mold, often weighing more than 20,000 pounds. They must be cast in one large piece for use in fabricating large structural parts for cars and airplanes. If they crack while being made, they cannot be used for manufacturing purposes. Even if recycled, it can cost tens of thousands of dollars. So that's just kind of some baseline information. In one plant, only about 20% of the ingots were cracked. The plant engineer tried out a new process hoping to reduce cracking. So here's some more information about this new process. Since then, 400 ingots have been made and only 17% of them have been cracked. Has the cracking rate really decreased, or is the 17% just a fluke? So that's our main question that we're going to test using a hypothesis test is, has the cracking rate really decreased? We can treat the 400 ingots cast with the new method as a random sample. Each random sample should have a somewhat different proportion of cracked ingots. Is the 17% we observe merely a result of natural sampling variation? Or is this lower cracking rate strong enough evidence to assure management that the true cracking rate now is truly below 20%? Well, to answer this question, we need to learn how to test hypotheses. So we're going to break down our process. Every time you do a hypothesis test, this is going to be your general 4-step process. State your hypothesis, then check your conditions so that you can use a normal model, then actually run the mechanics. This is like the math portion of it. You're going to calculate a z-score, you're going to find your p-value, and you're going to use either your, that should say blue sheet, so let's change that to blue sheet, or calculator. In other words, look up your percentage on your blue sheet. And then finally, based upon your percentage, you're going to state your conclusion. So what we're going to do is we're going to go through a series of slides that breaks down each one of these steps and explains each one of them in further detail. So let's start by looking at the hypothesis stage. So step 1 is you need to state a hypothesis. For every problem, you're going to break it down. So here's the general rule for what a hypothesis is. It is working models that we are adopting temporarily. And then there's 2 types of hypothesis that are used in every test. So let's look at these 2 types of hypotheses. The first hypothesis that you're going to write every time you do testing is what's called the null hypothesis. The null hypothesis is the claim that's being assessed in a hypothesis test. It has a special notation. We are always going to use H sub O, H sub 0, to denote the null hypothesis. This hypothesis specifies a population model parameter of interest. Notice it says we're focusing on a population parameter. So we're stating up front, here's a specific number for the population and proposes a value for that parameter. So the way we always write the null hypothesis, you're going to have H sub 0 and you're going to have colon. Your parameter is always going to be, because this is proportions in this chapter, it's always going to be P equals for the proportion, and then you're going to write down the original value that we know for the population. Then we have the alternative hypothesis. This is what we think has changed. Okay, this is what we propose, what we should conclude if we find the null hypothesis to be unlikely. So this is going to be specific to the problem. It can either be one of three different types. It can be a not equal to, it can be a less than, or it can be a greater than. So we could simply be saying that the original value is no longer possible. That's a not equal to. We could claim that it is now lower than the original value, or we could claim that it is now higher than the original value. And we're going to dive a little deeper on the next slide into this alternative hypothesis. So the null is h sub 0, and then p equals some value. So now let's look at the alternative. So there's two types of alternative hypotheses. The first one's called a one-sided alternative. This specifically focuses on deviations from the null hypothesis in only one direction. So the first type of null hypothesis would be h sub a. We call this the alternative. That's why we use the letter a. The parameter, which would be p, and then is less than whatever your original value is. The other one-sided would be h sub a for alternative hypothesis, and it would be your parameter is now greater than the original. And so when you read through the problem that you're being asked to evaluate, you'll know which symbol to use there. A two-sided alternative basically puts both of the one-sided together. It focuses on deviations on both sides, lower and higher. And so the way we would write this is h sub a for alternative hypothesis. Parameter is simply not equal to the original hypothesized value. So now we're going to go back and we're going to look at our example. Okay, so we were talking about the ingots. So to test whether the changes made by the engineers have improved the cracking rate, we assume, first of all, that they have made no difference, and that any apparent improvement is just sampling error. So our original hypothesis, h sub 0, is based on the original percentage of cracking rate. And if you go back and you look at that first slide, it said in one plant, only about 20% of the ingots were cracked. That 20% is what we are using for our original hypothesis. So h sub 0, we write h sub 0 colon, and we're saying that p equals, and we simply take the 20% and we write it as a decimal, 0.20. Now, what would our alternative be? Well, we kept asking, if you look back at, again, our original problem, the new sample had a 17% cracking rate. What we were wanting to know is, has the cracking rate really decreased? So decreased means it has gone down. So going down means that we're looking at a less than problem. So our alternative, since we want to see if the cracking rate has gone down, our alternative is that P is now less than 0.20. So our original is that P is equal to 0.20. That was the original stated proportion. And now we're going to test to see if it is lower than 0.20. So anytime you're doing a hypothesis, that is how you set up your original two hypotheses. So now let's look at more detail on the second of the process. This is simply the checking conditions. This is the part that you should be familiar with. So the conditions that we have to check are the same conditions that we've checked before. Is it random? Have we met the 10%? And are NP and NQ both bigger than 10? If for some reason any of these conditions are not met, you can't go on, you stop right there, you simply say we can't test. If the conditions are met, we're going to run a 1 proportion z-test like we learned in the last chapter. So let's actually test our conditions. So first of all, is it random? It said in the original problem the ingots were chosen randomly. No problem. 10%. Well, our sample was 400. And if you remember, all we do is we tack on a 0. And so these are things that are used for all cars and planes. So it is definitely something that is commonly used. And so to say that there's 4,000 of them is a very safe assumption. In P, so we take the 400, we're multiplying by the 20%, and we get 80. Well, that's bigger than 10. In Q, we're taking the 400, and well, 100% minus 20% leaves us with 80%, and those give us 320. So we have met all three of our conditions, and so we are good to go on to now the math portion. So let's take a look at the next slide. So step 3 is the number crunching. It's the mechanics. You have two things to find. You first have to find your z-score, and then you have to use your blue sheet to find your probability. So let's look at the necessary formulas that you will need to use here. So the first formula, you'll need to know the mean. Well, the mean is the original p-value that we used and were given. What's the standard deviation? Well, the standard deviation is always square root, and we've seen this formula before, p times q divided by n. Once you have those two, then you can go on to your z-score. Remember, this is your new p hat. That was from the sample. This is from your population. And this is, of course, your standard deviation. So let's go through our steps for calculating our z-score. So what do we need to know? Well, first we need to know our p-value, which is 0.20. And our p-hat that we're going to be testing was the new one from the sample, which was 17%, or 0.17. Let's calculate our standard deviation. So p is 0.20 times 0.80 divided by, and our sample size was 400. And so if you type that in the calculator and you round, I get 0.02. So now we need to calculate our z-score using our little formula. So p hat is 0.17 minus p, which is 0.20, divided by the standard deviation of 0.02. If you round, I actually get an exact answer, but it would be negative 1.5. And so because we need two decimals, I'm going to tack a little 0 on right there. So let's think about our blue sheet and what we're going to have to look up. We know 0 is in the middle. We know negative 1.50 is over here. Think back to our alternative hypothesis. When we did HA, we did less than, which means we're shading to the left because we want to know if it's gone down. So all you have to do is go to your blue sheet and look up negative 1.50. So go to the negative side, go down to negative 1.50, and I get 0.0668. So that is what I call my p-value. So your p-value is going to now help you decide on your conclusion. So let's look at the details for the conclusion. So when we make a conclusion about our hypothesis, we have two different options. We're either going to reject the original hypothesis. To reject it simply means that there is enough evidence that the alternative hypothesis is plausible. And here's the simple rule. This occurs when your p-value that you got from your blue sheet is less than 0.05. That's going to be the general rule. Well, that's rejecting. There's also failing to reject. If we fail to reject it, that means that there is not enough evidence that the alternative hypothesis is plausible. In other words, our test didn't prove that there was enough difference. This occurs when the p-value from the blue sheet is greater than 0.05. And so ours was 0.06, which is definitely greater than 0.05. And so our conclusion, and you don't gotta write a big long sentence, our conclusion is simply, since P is 6.68%, or if we leave it in decimal form, 0.0668, we fail to reject the null hypothesis. So since, you're always going to say, since P equals this number, we either reject or fail to reject the null hypothesis. So now that we've kind of broken the process down step by step, now we're going to go through a couple of examples just to make sure you fully understand everything. So a large city's Department of Motor Vehicles claimed that 80% of candidates passed the driving test. So there's a percentage. But a newspaper reporter's survey of 90 randomly selected teens who had taken their test found that only 61 who had passed. So does this finding suggest that the passing rate for teenagers is lower than the DMV reported? So the first thing we need to do is state our hypothesis. So your original hypothesis, which is H sub 0, is always the original stated p-value. Well, that was 80% or 0.80. Then you have an alternative. So we know it's P, but then we come back over to our question and it says, does this finding suggest that the passing rate for teenagers is lower than the DMV reported? So lower means less than 0.80. The number doesn't change, it's just the symbol that does. So now let's check our conditions. So did it mention somewhere up in our problem about random? And it says randomly selected, so yes. 10%. How many were in our sample? Well, that was 90. Add on a 0. Do you think that there is 900 teenagers in the world? I would assume yes. So now we have to do NP and NQ. So 90 times our p-value is 0.80. So I get 72, which is a good number. And NQ, 90 times, well, the leftover is 0.20, which gives you 18. Why is my pen not working? There we go. And so all of our conditions are met. So those are your first two steps of your hypothesis. So now let's talk about the math part. So the mechanics. So the first thing we need to know is our p-value, and that was 0.80. We also need to know our p-hat. Well, it didn't tell us a number, or a percentage. It told us a number. It said that 61 out of the 90 passed. And so if you take 61 divided by 90 and you round to 2 decimals, I get 0.68. So there's our p-hat. So what's the next thing we have to find? We have to find our standard deviation. So square root, p is 0.80, q is 0.20, and our n was 90. And so if you type that in the calculator and you round, I get 0.042. So what's the next piece we have to find? If you think about your formulas after the standard deviation, we have to find our z-score. So it's p-hat, which is 0.68, minus p, which is 0.80, divided by our standard deviation, 0.042. We need 2 digits for our z-score, so -2 point, and it rounds to 86. So if we draw our model, and we always know zero's in the middle, negative 2.86 is somewhere way over here. Now, what were we trying to test? Less than or greater than? Well, in this case, we were still doing less than, so we're shading to the left. So pick up your blue sheet, go to the negative side, find negative 2.86, and I get 0.0021. So our conclusion, we start by saying since P equals 0.0021, now what was our cutoff? Our cutoff was 0.05. This is definitely less than 0.05. So if you need to look back at the rules, when it is less than 0.05, we reject the null hypothesis. And that's all there is to the conclusion. And so let's look at another example. Anyone who plays or watches sports has heard of the home field advantage. Teams tend to win more often than when they play at home. Or do they? If there were no home field advantage, the home teams would win about half of all games played. In the 2007 Major League Baseball season, there were 2,431 regular season games. Tied at the end of the regular season, the Colorado Rockies and San Diego Padres played an extra game to determine who won the wild card playoff spot. It turns out that the home team won 1,319 of the 2,431 games, or 54.26% of the time. Could this deviation from 50% be explained just from natural sampling, or is it evidence to suggest that there really is a home field advantage, or at least in Major League Baseball? So we need to state our hypotheses. Well, our original would be that the chances of winning are no different. In other words, that the home team should win 50% of the time, and the away team should win 50% of the time. The alternative, so now we're saying, could this deviation from 50% be explained just from natural sampling, or is it evidence to suggest that there really is a home field advantage? Which means home field advantage is you have a better chance of winning. So that means that P is greater than 0.50. So now we have to check our conditions. So let's start with, whoa, I can't write. My pen's being dumb, sorry. Random. So up in here, it's talking about an entire season. So the nice thing is, because it's talking about an entire season, all of the games were used, so random is perfectly fine to assume. So then 10%. Now you got to keep in mind, we've been playing baseball for well over 100 years. And so if we take the sample size of 2,431 and we tack a 0 on the end of it, do you think there's been 24,000 baseball games played in Major League Baseball? I mean, we selected only the year 2007. There's been hundreds of years. And so we can definitely say that there has been that many games played with no problem. Okay, so what about NP? So remember, P is only 50%. So 2431 times 0.50. The nice thing is NP and NQ are going to be exactly the same. So what do we get for both of them? We get 1,215.5 for both of them. So they are both most definitely good to go. So now we have to do our mechanics, or our math. So let's see what we know. We know that P is 50%. It told us that P hat was 54.26. So that would be 0.5 5.426. So what do we got to calculate? We have to calculate the standard deviation. So we got 0.50 times 0.50 divided by 2,431. And if you rounded two non-zero digits, I get 0.010. So now we got to find our z-score. P hat comes first, so 0.5426 minus p, so 0.50, divided by the standard deviation of 0.010. Remember, we need two decimal places, so we get 4.26. So if we go and make our pretty little picture, we got 0 in the middle. 4.26 is way, way, way over here. Which way were we shading? Well, if you remember, this time our alternative was bigger than 0. So go to the positive side, and if you notice, there isn't a 4.26. But it tells you, or it should say, anything higher than, I think it's 3, you need to just use the same number at all times. And so they tell you that that number is 0.9999. Well, that's if we were shading to the left, but we're shading to the right. So we need to take 1 minus that answer, and we get 0.0001. And so our conclusion, since P is equal to 0.0001, do we fail to reject or do we reject? Well, if you have to look back at your rules again, if it's less than 0.05, which is the case here, then we reject the null hypothesis. Let's look at one last example. Advances in medical care, such as prenatal ultrasound examination, now make it possible to determine a child's sex early in a pregnancy. There is a fear that in some cultures, some parents may use this technology to select the sex of their children. A study from Punjab, India, reports that in 1993, in one hospital, 56.9% of the 550 live births that year were boys. It's a medical fact that male babies are slightly more common than female babies. The study's authors report a baseline for this region of 51.7% male live births. Is there evidence that the proportion of male births has changed? So our original hypothesis, H sub 0, is based upon the data for the whole population. So that's what we would consider the baseline data. So this 51.7% is your baseline data. So our null hypothesis is that P is equal to 0.517. Now, if you notice, the question is asking, is there evidence that the proportion simply has changed? It didn't say go up, it didn't say go down, it simply says has changed. So that means that our alternative hypothesis is the two-sided one. We're going to use the not equal to. In other words, it's simply not what we are proposing of 5.17 or 0.517. So we'll see how this is different in the math in just a little bit. So let's check our conditions. So the first condition, did we select these people randomly? And we are going to assume that yes, this was random. 10%. So how many births were there? 550. Add a 0 to that, we get 5,500. And yes, it is safe to assume that there are 5,500 births every year. NP, so we're going to take 550 times 0.517. I end up with 284.35. And then if we do NQ, we take 550 times. Now if you take 100 minus 51.7, you're left with 48.3 or 0.483. And I get 265.65. So both of those are bigger than 10. All of our conditions are met. So now let's go on to our math. So what do we need to know math-wise? We first need to know our p-value, which was 0.517. We need to know our p-hat. So for that one sample, it was 56.9. So 0.569. So we now have to find our z-score. I'm sorry, we have to find our standard deviation. So we're taking big square root 0.517 times 0.483 divided by our sample size of 550. And if you rounded two non-zero digits, you get 0.021. Now we can find our z-score. So p-hat goes first, 0.569 minus p, 0.517, divided by 0.021. So if we round that to two digits, I get 2.48. So let's talk about how this one is different because of the not equal to. When it's not equal to, you actually use the positive and negative z-score. So the positive, which was the 2.48, is over here, and the negative is on the left side. And instead of shading just once, we shade twice. In other words, we shade to the right on the positive one and to the left on the negative one. Well, we know both of them are going to give us the same results. So what we do, because it's always easier to look up negative left sides, we go to the negative side and we look up negative 2.48, and you should get from your blue sheet 0.0066. But since the other one is exactly the same, all we're going to do is double that amount, which gives us 0.0132. So let's write our conclusion. Since p is equal to 0.0132, we, if you remember, this one is also less than 0.05, so we are going to reject the null hypothesis. And that example is done.